Hello, my name is John Baxter. I'm a computer science graduate student and part of the Tapia lab at the University of New Mexico. Here I will be presenting our research work, exploring learning for intercepting projectiles with a robot-held stick, to be published in the Proceedings of IROS 2021. In this work, we analyze a problem in which reinforcement learning is used to control a robot arm tasked with intercepting a projectile with a stick. We go in depth into the question of what types of robot state observations produce robot interception control policies that are fast to train, have good performance, and are resilient in a variety of untrained-for situations. Consider the case of a robot, in this case modeled after a KUKA arm. The robot arm is equipped with a stick, which is attached to its end effector. A control policy must be learned that accelerates robot joints such that the stick intercepts a projectile. Interception is a hard problem. This is because an agent must determine two things quickly: when and where to intercept the target, and how to move in order to intercept the target. Interception is worth studying because it is a building block of many tasks, including catching and juggling, batting, and parrying. Our contribution is the following. It is well known that input feature choice is critical to learning. There are two natural choices for representing a robot state to a policy: the robot's joint angles and the spatial positions of the robot's links. To the best of our knowledge, no one has previously done a thorough analysis of which is better in the context of interception problems. Before going further, we will define what we mean by robot joint angles, or joints for short, and robot link positions, or links for short. By joints, we mean angles between articulated bodies measured relative to rest positions. In our work, all robot joints are simple revolute joints. By links, we mean the Cartesian coordinates of reference points on the robot's rigid bodies. In our study, there are 7 link positions corresponding to the center of mass of the robot rigid bodies beyond the base, as well as 3 link positions placed at the endpoints and center of the stick used for interception. An obvious question is what robot representations are commonly used in reinforcement learning. We will go over a few representative related works. In a stick parrying task, Wang et al. Fed a deep Q network of joint angle observations over the most recent 4 frames. Bansal et al. Used joint angles and velocities, along with contact forces and the relative position between agents, in a variety of multi-agent competitions. In reinforcement learning for table tennis, Majorian et al. Used observations of the joint angle and velocity, as well as several observations of the end effector paddle state. In another table tennis reinforcement learning work, Gao et al. Gave their policy joint angles over the most recent 8 frames. We can see that joint angles are typically given in robot reinforcement learning, usually with temporal joint information such as joint velocities or joint samples across multiple frames. This is sometimes augmented with additional information. We are studying the utility of these 2 representations as input feature choices for deep reinforcement learning. Here we will explain the structure of the deep neural network evaluated. The input at each step is the ball position plus the chosen robot observation features for the 1 or 2 most recent stimulation time steps. Our network has 4 fully connected hidden layers of 256 neurons each with ReLU activation. The network outputs at each time step robot joint angle accelerations. Furthermore, we train using the PPO algorithm with the Atom optimizer, use actor-critic with identical hidden layers without shared parameters, and train each policy for 1 billion time steps. Actions are discrete accelerations applied to joint angles. The reinforcement learning task has 4 terminal events. First If the projectile hits the ground, the episode terminates with a -1 reward. If the projectile hits the robot, the episode also terminates with a -1 reward. A -1 reward is also given if the robot hits itself with its stick. Finally, a +1 reward is given if the stick hits the projectile. This event will be called success from here on. We perform reinforcement learning experiments in which we vary whether joint angles, link positions, or both are used as robot observations, and whether 1 or 2 frames of observation are given. I will use combined type as a synonym for both from here on. In addition to evaluating learning over the course of training, we perform 3 post-training experiments in which we present the trained policies with untrained-for projectile speeds, Gaussian projectile position observation noise, and Gaussian projectile accelerations. Here we present training results. In the x-axis are time steps of training. In the y-axis is the success rate, or rate at which the stick hits the projectile. We see that joints 1 frame reaches an 85% success threshold at around 370 million time steps. By contrast, links 1 frame reaches the 85% success threshold by around 200 million time steps. Joints 1 frame reaches an average success rate of about 89% compared to 92% for links 1 frame. Thus, in the 1 frame case, link observations learn faster and reach better performance than joints. We will now consider 2 frame cases. Here, joints 2 frames takes about 610 million time steps to reach 85% success rate compared to 270 million time steps for links 2 frames. At the end of training, joints 2 frames reaches an average success rate of only 86% compared to links 2 frames at almost 97%. Therefore, for 2 frames, the gulf between joints and links widens, again with links learning faster and reaching better performance than joints. Comparing 1 frame to 2 frames, with joints, moving to 2 frames increased time steps to reach 85% success by 240 million time steps. For links, moving to 2 frames also increased time steps to reach 85%, but only by 70 million time steps. Of great interest, moving to 2 frames decreased final performance for joints, but increased final performance for links. Thus, links are superior in training, with links 1 frame best for fast learning and links 2 frames best for final performance. An obvious question is then, how do links compare with a policy trained with combined joint angle and link position observations? Combined 1 frame reaches 85% success rate at about 5 million time steps sooner than links 1 frame, while combined 2 frames reaches 85% success rate about 25 million time steps sooner than links 2 frames. Combined 1 frame's final success rate is about 95%, greater than links 1 frame's 92%. However, for 2 frames, links and combined each reached about the same final success rate, near 97%. Compared to links, policies with combined joints and links reached better final success for 1 frame, while for 2 frames the policy learned a little faster. We will now examine how each observation type handles untrained-for dynamics and noise. Each bar shows results for a different robot observation and frame count combination. The height of the bars denote success rate. In training, all projectiles had a fixed horizontal speed of 3 meters per second. Here we compare against the case where the projectile's horizontal speed is chosen uniformly at random in the range of 1 to 5 meters per second every episode. Performance is lowered for all observation types when exposed to these untrained-for dynamics, however some do better than others. The most resilient are the 2 frame links and combined types. followed by the one-frame links and combined types, while joints one-frame, and especially joints two frames, generalize poorly. The most plausible explanation is that policies with link observations learn to minimize projectile stick distance, while policies with only joints learn mappings from joint angles, projectile position combinations to robot actions, which would be expected to be more brittle. We now consider the case where Gaussian noise is added to the projectile's observed position each time step, while leaving projectile dynamics unchanged. Combined type observations are especially resilient here. For links alone, two frames handles noise much better than one frame. Finally, for joints, this is the one case where joints two frames outperforms joints one frame, although they both do rather poorly. Multiple frames in general seem to be associated with greater resilience in the face of observation noise. It seems that extra frames and extra observation types produce less brittle policies in the face of observation noise. Finally, we consider how the policy types handle random, untrained-for Gaussian accelerations applied to the projectile. The results are qualitatively similar to those of the random horizontal speed experiment, with two frames links and combined performing best, one frame links and combined in the next tier, and joints one frame doing slightly better than joints two frames, which performs the worst. Again, we speculate that policies with link observations are learning to minimize projectile stick distance, while policies with only joints are learning a less resilient mapping. To summarize, compared to joint angles, link position observations resulted in faster learning, better performance, better ability to utilize multiple frames, and had more resilience to noise. Additionally, relative to link positions only, policies with combined joint angles and link positions had better performance in the one-frame case and faster learning in the two-frame case, and in terms of projectile position noise, were more resilient. So why are link positions important for interception tasks when it is known that the rigid link positions of an articulated body can be calculated from the joint angles anyway? We believe this is because projectile observations and link positions are both spatial coordinates, allowing the policies with links to more easily calculate the distance of the projectile from the robot body, which must be kept at a safe threshold, and the distance of the projectile from the stick, which must be minimized. In the joint angle only case, networks must first emulate a kind of forward kinematics to get these positions and distances, and may therefore either have fewer remaining network parameter resources to use for control decisions, or else may eschew distance calculations entirely and instead learn rigid pattern matching between observation input and robot motion output. I hope this has been an interesting look at how and why different robot representations affect reinforcement learning for interception. Code, scripts, and trained policies related to this project are available on our lab's website.